CapeSim is developing a new tool to facilitate the production of device templates from GDSII layout files. Let's preview this capability by modeling a heterojunction bipolar transistor. Now I've already created a layout for the device and saved it as a GDSII file. So I'll just open this file in the new tool, and what's displayed are the layers that are defined in the file. Now I can't edit this artwork in this tool, but I can go in and edit the display of the layers. So here you see the layers that are defined in the file, and I can, for example, go in and change the display to show field patterns, and if I wanted to I could go in and change the color of a layer or other things. And these first two layers, layer 1 defines the subcollector layer, and layer 11 defines the collector metal on top. So now you can see those two shown as solids. Now the second thing we need to do is to define the materials that we want to use in the template. And one way to do that is just load in the materials from an existing template. So I'll just load in all the materials from the generic FET. Now if we wanted to, we could go in and edit this materials list. We could change any of these materials, their properties, or add a new material, for example. But I'll just keep the materials list as it is. Then the final thing we need to do is define the process that takes these layers and materials and creates the actual 3D device. So if we edit that process, it brings up the process definition table, and this shows the layers that are in the GDSII file, but no process yet defined. So let's just start by defining a process on a couple of layers. So on the subcollector layer, we'll assign it a material of gallium arsenide, and this will be a 1 micron thick mesa, and we'll call it subcollector. And the layer with ID 11 will be the collector metal. We'll also make it 1 micron thick. And we could go through and basically define all the layers in the process. Now, rather than going through all that, I'll load in a process table that I've already created that has the layers defined. And so if we look at this more complete table, what we see is first we have the subcollector and the collector metal, and then we have the collector base, the base metal, the emitter cap, emitter metal, and all the bus metal, the passivation layer underneath the emitter bridge. So we have basically most of the steps defined, and if we want, we can fabricate this device and see what it looks like in this tool. So basically we can take and convert those layers and their thicknesses into a 3D model, and this 3D model is what we're going to generate as a template. So here's the device. We need to define a few more things, so let's go back into the table, and the first thing I want to do is create a couple of layers to define the substrate and the backside metal. So I'm going to create a layer here before layer 1, and this will be a gold layer, 10 microns thick, and this will be the backside metal. Now, I made it gold, but later we could change that to some other material when we run our simulations. And then the second layer that I'm adding is the substrate. So that's gallium arsenide, 100 microns of gallium arsenide. So the next thing we want to do is we want to actually indicate that these two layers that we just added are part of the MYMIC. In other words, they're the common layers whenever we create an integrated circuit. So we just do that by checking the boxes associated with that, and then we need to find where the heat is generated. So we'll say that the power is dissipated in the emitter layer. So then we've defined our device, and we can fabricate it, and here's what it looks like. So now it's completely ready to go, and we can just write out a template for it. Now if we go into SYMMIC, we can open the template that we just created, and we can go in and now use it like a regular template. So we can go in and change the materials on any component. For example, if we wanted to change the substrate to a different material, we just go in here and select the new material that we wanted to use, or we could even define new materials if we wanted. Um, we can go in and change the thicknesses of some layers. For example, we could change the thickness of the substrate, um, or the backside metal. We can change the amount of power that's dissipated, or the environmental temperature in the backside film parameter. And once we've set it up the way we want, we can just say run simulation. And what it's going to do is use the template information to mesh this and do a thermal analysis on this device. So here's the results of our thermal analysis. And let me just add a mesh here, and you can see that we've done our thermal analysis and we've gotten our results, and we have our peak temperature. And if you want, we could plot a max temperature for that device. And we could create a layout for this device where we, for example, examine what would happen if we put several of these devices close together. And now I've already done that, so I'll just open up the layout that I already created, and here's 4 of the devices together, and we could run that or load in the solution that I already have and plot the results. And you can see the additional heating by putting these devices close together.